Good morning, Trailblazers. Well, some of you will hear this in the afternoon, so I guess I should just say, happy Thursday. I'm not calling or making this video from somewhere really exotic, like North Carolina this time. I'm just here in Houston. I'm just taking the lab aides on a field trip, but I wanted to make sure you guys are prepared for the test tomorrow, so I went ahead and made a good test review handout as well as a video. So we're starting with the bell ringer. You're not going to do this on the bell ringer sheet that we normally do. At the top of your test review that you grabbed when you walked in the door, it says there's 4 signs of a chemical change. I want you and a partner, you can work with a partner and discuss this if you like. See if you can list the 4 signs of a chemical change. This shouldn't take that long, so I'm going to give you 2 minutes, starting now. Go. About 30 more seconds, you guys should be done. Alright, I'm going to go ahead and put the 4 signs of a chemical change on the board, and you guys can take a look. Okay, so there are 4 signs of a chemical change. The first one is absorbing or releasing energy. So that's like any sort of temperature change. It should feel hot or cold to the touch. If you see light or you hear sound, that's usually a sign of energy being released. Formation of a gas, so you see any bubbles forming, if you smell anything, right, those are all examples of a gas being formed. Color change, that one's pretty self-explanatory, and then lastly, the formation of a precipitate, which is a solid solid formed when 2 solutions are mixed together. So I just wanted to point those out to you because there will be questions on the test tomorrow about physical and chemical changes, and sometimes they're kind of tricky, but just keep in mind the 4 signs of a chemical change. Okay, so on physical and chemical changes, there's going to be 3 questions total. Before we get started for real, I just want to make sure that everybody has out a periodic table. So I'm going to give you 30 seconds, take out a periodic table and this test review, and that's all you need. You don't need anything else. You should be taking out a periodic table now. Alright, let's move on. I wanted to show you this diagram one more time before the quiz tomorrow, or for the test tomorrow. I think particle diagrams usually give students the most trouble, so on your review I've given you 4 boxes there so that you can draw this little particle diagram, this diagram here, and this diagram down here. So I'm going to give you 1 minute to draw these diagrams. They don't have to be perfect, just the same general idea that you have there. So I'm going to give you 1 minute. I want you to draw both the physical change boxes up top and the chemical changes on the bottom. So 1 minute starting now. Alright, so let's just talk through these diagrams one more time before we move on. Remember, a physical change is just a rearrangement of the particles. You have the same number and the same configuration of particles. So you have 3 black dots together, or 3 pairs of black dots together on the left side, and you have 3 pairs of black dots together on the right side. On the left side of the physical change, you also have 2 pairs of white dots on the left side, and then 2 pairs of white dots on the right side. If you can see, all it is just a rearrangement. Like, it looks like this is a gas here, with the particles kind of being really far apart, and it's gone to like a liquid or a solid, where the particles are more arranged in a more organized way. A chemical change also has the same number of total particles, like there's 6 dots on the left and there's 6 dots on the right, but they've been rearranged and configured in a new sort of product. Right, so this would be like, I think we talked about the formation of water, where the white dots would represent the hydrogens and the black dots would represent the oxygens. And then as it comes over to the product side, now you have the actual water molecules with one oxygen and then 2 hydrogens attached on each particle. I also just want to quickly go over the examples of the vocabulary. Physical changes: melting, freezing, tearing, dissolving, shattering, boiling, crushing. These are all reversible, right? If you melt something, you can unmelt it. I guess that would be freezing it. If you tear something, you can like fix it, put it back together. Those are all examples of physical changes. While chemical changes are not reversible easily. So like if you burn something, you can't unburn it. If you explode something, you can't unexplode it, and so on and so forth. So I just wanted to point that out before we move forward. Alright, we're going to try a physical-chemical change question, then we're going to move on to a different topic. Alright, so here it says question number 2. Which set of procedures and observations indicates a chemical change? So this would be where you're looking out for those keywords here. Alright, so we're going to be looking for things like that are not reversible. Alright, so look at question 2. Why don't you take I don't know, let's take 60 seconds to read it, and then we'll go try to answer it together. Alright, 60 seconds starting now. Uh-oh. Sorry, hold on 1 second. Sorry about that. I'm learning how to draw on this thing, so I'm still having some growing pains. Continue. You have about 40 more seconds to finish this problem. Okay, so if we're looking at this, we're just going to go through each answer choice and I guess eliminate the ones that are wrong. So F says ethanol is added to an empty beaker and then the ethanol eventually disappears. That's called vaporization or evaporation, which is not a chemical change because the ethanol is really just changing to a gas, so there's no chemical change happening. There's nothing about burning, there's nothing about bubbling, nothing like that. Part G, a solid is gently heated in a crucible and the solid slowly turns to liquid. So this would be an example of melting, right? They didn't say anything about, bubbling. They didn't say anything about precipitates. That was no good. It says fine blue crystals, this is part H, fine blue crystals of crystal 2 sulfate are added to water and dissolved to form a blue solution. Watch out for this word dissolve. That is a physical change, not a chemical change. It is often confused for a chemical change, but it is not. Dissolving means that it is a physical change, because if you want to not dissolve something, all you do is heat it up and the water evaporates and you're left with the solid, so it's still there. Example J, large crystals are crushed with a mortar and pestle to become powder. Again, no signs of a chemical change there. So obviously our answer is K. And the key part of K that really helps us is the bubbling, right? When they talk about bubbling, that's the formation of a gas. So that's why K is the answer, because it is an example of a chemical change. Okay. So now let's go to the next question. All right, nuclear changes. I'm going to fill in this chart, and I want you guys to fill in the parts that are blank on your sheet. I'll give you, let's say, 1 minute to fill this in. Okay, so these are the 3 types of particles for the nuclear decay equations. I just wanted to make sure you saw them again before we started writing nuclear decay equations. Remember the helium here is a representative of an alpha particle. It's the largest one and the weakest, so it moves very slowly. Betas are really fast, but very small, where it's almost nothing. It's just an electron. Remember, electrons are very small and don't have a lot of mass. And then gamma particles actually have no mass at all. That's just pure energy being released. So that's where the 0, 0 comes from. Make sure you can recognize the E and the B for beta, and the helium and the alpha for alpha. It could be written either way tomorrow on the test. But you need to know that alpha is 4 and 2, and then beta is 0 and -1. And then gamma obviously is 0 and 0. Okay, so now we're going to write a few nuclear decay equations, and you guys are going to get a chance to practice this a little bit. So let's start with the nuclear decay equation for for uranium 238. So the first part we have to do is we have to write uranium 238. So we write the U for uranium, and then remember this number after uranium is the mass number, so that's the number that goes on top. And if I look on the periodic table, uranium is element 92, so I put a 92 for the atomic number. It says it's decaying, so that means it's breaking into 2 pieces. And I know what one of those pieces is going to look like, and then I have to figure out the other piece. I know one of them is going to be an alpha particle, so now I'm going to draw my alpha particle. Alpha particles have a mass number of 4 and an atomic number of 2. And then I wrote helium, but you could draw the fish for alpha if you really wanted to. And now I have to use the top numbers and the bottom numbers to figure out what my new particle would be. Well, remember the total on the left and the right has to be the same. So the mass number is 238 on the left, which means my mass number for my missing particle is going to be something plus 4 to give me 238. So what plus 4 gives me 238? Well, obviously it's 234. So that's where my mass number comes from. So again, 234 plus 4 is 238. And so it's 238 on both sides. It has to be equal on both sides. The same thing applies for the atomic number on the bottom. If I have 92 on the left, then I need to have 92 on the right. So I would ask myself, like, what plus 2 gives me 92? And it would be 90. So 90 is my atomic number. And if I look on the periodic table, that's thorium. So I write the TH for thorium. At this point, for some reason on the quizzes, people were like just boxing this, right? You need to box the whole thing. Like the whole thing is your decay equation. So if you're going to box an answer, which you don't have to, by the way, the whole thing would apply because that's the whole nuclear decay equation. Just a little tip. All right, next part. Oh crap, hold on one second. Okay, I fixed it. All right, so now we have to do beta decay for iodine 131. So we're going to write iodine 131 first. So why don't you guys go ahead and do that. Take 15 seconds, write iodine 131. Alright, so you should have written an I for iodine. 131 is the mass number, and then the atomic number for iodine is 53. And it's undergoing beta decay. Why don't you guys draw a beta particle on the right side? I'll give you 10 seconds. Okay, a beta particle looks like this. You should have a 0 and a -1. -1 goes on the bottom, not the top. And I put an E for electron, but you could have also drawn the B with a little tail on it. Okay, so now we have to figure out what the missing particle is. For the mass number, this one's really easy because on the left side it's 131, and on the right side it needs to be 131. So 0 plus what gives you 131, and obviously that's 131. Now watch out for the atomic number. On beta particles, the number is -1, so it's actually a little counterintuitive. It needs to equal 53 on both sides. So if it's 53 on the left, then that means something something minus 1 needs to give me 53. So what minus 1 gives me 53 is 54. So 54 minus 1 is equal to 53, and that's why this number actually goes up, not down like the rest of them. Alright, so now I look on the periodic table. What is element 54? It's xenon, so now I'm going to get the Xe for xenon. Okay, hopefully this is coming back to you. We're going to do one more. Alright, so write the nuclear decay equation for the emission of a gamma ray at carbon-14. I'm just going to give you guys 1 minute. Why don't you do this whole thing by yourself, and then we'll just check our answers. So you have 1 minute. All right, let's do the nuclear decay equation for carbon-14. So we're going to write carbon-14. So that's a C with a 14 and a 6 for carbon. It is decaying through gamma decay, which is the easiest kind to calculate because it's 0 and 0. You can just draw a Y for gamma. I mean, it's technically a gamma symbol, but if you draw a Y, that's fine. All right, plus, so now we need to figure out what these top and bottom numbers are. So since this is 0 and 0, obviously it's the same atom on both sides. So a lot of the time students are like, what's the point of gamma decay? Well, it's just getting rid of energy, right? It's not changing the particle, but it still releases a lot of energy, and it is a lot of energy. It's very harmful to humans. So I don't write, if they ask you to write about it, that nothing happens, because something is happening. It's giving away energy. Yes, the atom isn't changing. It's not changing the carbon, but it is releasing energy. Okay, we're going to play a quick game called Name That Particle. I'm going to list pieces of evidence, and then I want you to name the particle. I want you to work with a partner during this time, see if you can figure it out. I'm probably going to do like 10 seconds between each clue. So let's, the answer is either alpha, beta, or gamma. All right, so let's start. So yeah, without using your notes, so go ahead and turn your sheet over. Okay, honor system, because I'm not there to check. Okay. It's a form of electromagnetic radiation. So is it alpha, beta, or gamma? Think to yourself. It has no charge. It has no mass. You should be getting close by now. It's released when the nucleus has too much energy. It's the most powerful radioisotope and requires you to protect yourself with lead. And obviously we're talking about gamma particles, okay? Especially this part, no charge, no mass. That should be a dead giveaway that it is a gamma particle. Alright, so we're going to do alpha or beta next. Okay. Has a charge of +2. Is the weakest isotope, radioisotope. It weighs 4 AMUs. It's emitted when an atom's nucleus is too large. It's represented by a helium atom. You should have it by now. It's an alpha particle. It looks like this, right? It could be 4/2 helium or 4/2 with an alpha symbol. All right, the last one has a charge of -1. You should already know it. It weighs 1/1840 AMU. You can protect yourself with a plastic sheet. It's emitted when there's too many neutrons in the nucleus. It's a beta particle. Beta particles look like this. Okay, so you should be able to, based on the description, identify an alpha, beta, or gamma particle, right? Just remember betas are negative. That's usually what they ask about. All right, moving on from nuclear. Now we're going to talk about writing and balancing reactions, which is a total of 9 questions on the test. So this is the bulk of the test. All right, so you should turn the page. We should be on page 2 now. You guys haven't had a lot of practice answering multiple choice questions about writing and balancing reactions, so I thought I would do a few of those, and then I'd let you guys practice a little bit, and then there's some traditional writing reactions problems on there. So what I want you to do, I want you to, by yourself, just try to answer this multiple choice question. I'll give you 1 minute to read it and see if you can answer it. Alright, let's go ahead and take a look at this one. So this one could be tough because it's a lot of like vocabulary words that some of you guys might not be familiar with. So it says the chemical equation is balanced when the coefficients of the reactants equal the coefficients of the products. So what that would mean is that like the number in front of each one is equal to the number in front of each compound is equal to the number in front of each compound on the right and left side. Which sounds like a good answer, but it's really not, because you could have a different coefficient. Like sometimes the coefficient is 4 on the left and 2 on the right, so that one's no good. Grab my little pen here. No good. Okay. B. Same number of each kind of atom appears on the reactants and the products. Okay. C. Products and reactants are the same chemicals. That would not be a chemical reaction. That would be a physical or a chemical change or physical change. So that one is not useful at all. That's like this hydrogen gas goes to hydrogen gas. That's not a chemical change at all. All right. D. Subscripts of the reactant equal the subscripts of the product. So that means that the little numbers. So it's like if it was like Cl2. And then you need to have a 2 on the other side too. That doesn't make any sense. The subscripts are just the little numbers. That's meant to test like if you know what subscripts are. So that one's not right. E. Total number of molecules on each side of the equation are the same. So this is really testing the difference between molecules and atoms. So the answer is B. Because you need to have the same kind of atom, or the same kind of atom on the left side and the right side. So you need to figure out the number of chlorines and chlorines on both sides, or bromines and bromines on both sides. Molecules would means like a combination, so that could be like something like H, Br. They would expect you to have also H, Br on the other side. Right? That's a molecule because it's a collection of atoms, and that's not an example of a chemical change. So you can see nothing's changing there. As opposed to here, you can have like an H, that's not a very good H, plus Br, right? And then on this side, you could have like H, oh geez, not my best work here. Let me try this again. Okay. As opposed, so this is for question B, right? This pen thing is nuts. Okay, try this again. One more time. Great. Let me draw it. Okay, here we go. H. Really having fun today, aren't I? H plus Br. Okay, and then that gives us on the left side H. B. Yeah, it's good. B and R. Okay, so you can see there you have the same type of atoms on each side. You have an H and a Br, and one H and Br. That's the same kind of atom, right? Not the same type of molecule, so that's why B is the answer. That was fun. Okay, next question. Sorry, I'm still drawing. Oh. Okay. This is another example of a multiple choice question you could be asked on the test tomorrow. This is like a very common type of question where it's like missing the reactant. So see if you can figure out which one you're missing. And basically what you should do here is draw your line. So you're going to draw your line underneath and then just count up what you have and then which one of these makes sense in terms of what you need. So figure out how many you have on both sides and then tell me which one would make sense or would balance the reaction. I'll give you a minute. Let's say 2. You got 2 minutes. Okay, well, the first thing that should have stuck out to you is that on the left side, you don't have any oxygen yet, right? You have hydrogens and chlorides, but you have an oxygen on the right side and then none on this side. So whatever your answer is, it needs to have oxygen. So right away, you can get rid of B, D, and E because neither of those have oxygen. So now you just need to figure out, do you need one oxygen or do you need two oxygens? So if you look here, you can see there's one oxygen on the water, but that 2 distributes to the oxygen as well. So it's 2 times the 1 O to give you 2 O's. So the answer is C because you need 2 O's and 1 lead on the left side. Hopefully that makes sense. Okay. I want you to work on questions 3 and 4 with a partner. If you finish, you can definitely move on to like a different part of the packet. There's tons of questions on here which I think are really valuable. The last thing I'm going to do is write a reaction with you guys and then let you practice on some. There are answer keys on your table, so if you want to check your answer keys for any of these questions, you certainly can. There's another 2 pages of practice after this. If you can do this entire packet without looking at your notes, you're probably in really good shape for the test tomorrow. If you would like some additional help, I will be here after school for tutorials from 4:30 to 5:15. I have to end early because I have the academic awards dinner tonight. So just stop by after school and I can work on some topics with you guys, whatever you would like to work on. You have 5 minutes. I want you to complete questions 3 and 4, and then if you finish, I want you to continue working. Don't just stop there. You have 5 minutes starting now. I'm going to set my timer, so if you hear a noise, that's what that is. So that's 5 minutes. The last thing I'm going to do, if you turn to the bottom of page 2, is I'm going to write one example reaction with you guys, as we've done many times this unit. And then you guys can work on anything you choose to work on in this packet for the rest of the class. So our reaction says, if heated, solid magnesium and water produce aqueous magnesium hydroxide and hydrogen gas. So let's break it down word by word. Let's start with solid magnesium, right? That's going to be our reactant. We're going to write that on the left side. So I write the Mg, and then I write the S to the bottom right in parentheses there to indicate that it is a solid. Then it says and, so and would be a plus sign, so I write my plus sign there. Then we have water. Water is obviously H2O, so I'm going to write H2O. And then anytime they don't specify, if they don't say steam or ice, it must be a liquid. So again, I write my lowercase l in parentheses to the bottom right. Produce. Produce is my arrow. Aqueous magnesium hydroxide. So there's my magnesium hydroxide, MgOH. And if I want to, if you're like, where did you get the parentheses from? Well, Mg is oh gosh, not this again. No G's. Okay, hold on. Guys, I figured it out. You just have to draw it when you pause it. So here is how I got magnesium hydroxide. Magnesium's charge is +2. Hydroxide is -1. So it takes 2 hydroxides to cancel out 1 magnesium. So that's how that happens. Okay. And then finally it says and. So it's another plus sign. And then hydrogen gas. So I write my hydrogen with a G symbol. Watch out for diatomics. Remember, a hydrogen is diatomic because it's one of the 7 elements. So I have to put a 2 there to the bottom right. All right, now that my reaction is written, I have to balance it. So I draw my line down the center. And I'm going to count up each side, magnesium and magnesium and oxygens and waters. So if I count everything up, I can see that on the right side I have 2 oxygens and 4 hydrogens, and on this side I have 1 oxygen and 2 hydrogens. So I just need to double my oxygens and hydrogens on the left side. So I put a 2 in front of the water, and that's going to double it to what I need to balance it. And so now I have a balanced reaction. There is one last thing I'm missing on this reaction, and it's the symbol, right? Heated. If it says if heated, then I have to put my triangle above the arrow to signify that heat is being used to make this reaction take place. Okay, again, if you would like to work on writing reactions, please come to tutorials today. There's 3 examples at the top of page 3, and I think there's even more on page 4. So there's also tons of practice in your packet, Unit 4 packet. I'm really confident about this test because we have been working on writing reactions for so long. I've got to work with a lot of you one-on-one about this. So you should feel confident too. If you want more practice, I'll be here after school. Please don't take my answer keys on the tables. I need those for the rest of class, so make sure you don't accidentally take that when you pack up today. Alright, you guys have the rest of class. It should be about 5-7 minutes to pick any sort of practice problem and work on it. If you have any questions, call or text me or come to tutorials. Thanks a lot, guys. Have a good day.